Hi, my name is Nick Seawald, and I'm a PhD candidate in statistics at the University of Michigan, and I'll be talking about sample size and time point trade-offs for comparing dynamic treatment regimens in a longitudinal SMART. This work is joint with my advisor, Danny Almirall. So I want to start with a motivating example from the field of addiction research. It's well known that it's hard to engage individuals with alcohol or cocaine-related substance use disorders in treatments. These interventions are effective, so clinicians really want these patients to re-engage with them after they've disengaged. So how should they do that? Should the strategy be to try and get them back into the original treatment, or should they give the patient some autonomy and perhaps offer them a choice of treatment modality? However, it's also known that for some people, these re-engagement strategies will work, but others will continue to not engage. So obviously, we'd like to get them into treatment, so we want to follow up with something for those folks who are continued non-engagers. So what if we do if the thing that we tried doesn't work? So this is a question about a sequence of treatments that is adapting to the individual over time, and this is how clinical decision-making often works. So a dynamic treatment regimen operationalizes this clinical decision-making process by recommending specific treatments to certain subsets of individuals at specific times. So this schematic is an example dynamic treatment regimen. Initially, this dynamic treatment regimen recommends that patients receive an intervention that we're abbreviating as MIIOP. This stands for motivational interviews with a focus on an intensive outpatient program. So this is basically 2 phone calls geared toward getting that participant back into their original treatment program. Then, if the participant sufficiently engages, according to some pre-specified criteria, the dynamic treatment regimen recommends no further contact for that individual. If the patient does not meet the criteria for sufficient engagement, then the dynamic treatment regimen recommends a second intervention, which is abbreviated MIPC, and this stands for a motivational interview with patient choice. So here the participant is given essentially a second set of phone calls, this time focusing on engaging them in a substance use treatment modality of their choice. So notice that the dynamic treatment regimen makes recommendations for both engagers and continued non-engagers. So it's tailoring subsequent treatment according to this engagement status. Now, often, scientists have questions about how to construct high-quality dynamic treatment regimens. And those questions can be addressed using a sequential multiple assignment randomized trial, or a SMART. A SMART's just one type of randomized trial that can answer these questions. The key feature of a SMART is that some or all participants in the trial are randomized more than once. So let's take a look at an example. This is a study called ENGAGE. The PI is Jim McKay, who's at the University of Pennsylvania. In the trial, the 500 individuals with an alcohol or cocaine-related substance use disorder who did not sufficiently engage in the first 8 weeks of an intensive outpatient program were recruited into the trial and were randomized between MIIOP and MIPC and then followed for 8 weeks, at which point they were determined to have either sufficiently engaged or they continued to not engage. This was determined using pre-specified attendance criteria. So everyone who engaged was given no further contact, but they were still followed for research outcomes. On the other hand, all continued non-engagers were randomized a second time, this time between MIPC and no further contact. Everyone was followed for a total of 24 weeks. And over the course of the study, for our purposes, continuous outcome called treatment readiness, which is a measure of a participant's willingness and ability to engage in treatment, was measured at baseline and weeks 4, 8, 12, and 24. Now, you may have noticed that there are dynamic treatment regimens that are embedded in this SMART, and there are 4 of them, actually. Here's the one that we saw earlier, which recommends MIIOP initially, then no further contact for engagers, and MIPC for continued non-engagers. So individuals who end up in subgroups A and B at the end of the trial are consistent with this regimen. Similarly, here's another one, and another embedded regimen, and a 4th. So there are 2 things I want to point out here. The first is that engagers are consistent with 2 embedded DTRs, whereas non-engagers are only consistent with 1. Notice here that subgroup D lights up in both yellow and blue, but subgroups E and F only light up once. The second point is that engagers are only randomized once at the beginning of the trial, but non-engagers, continued non-engagers, are randomized a second time. Both of these things need to be accounted for in our analysis of the data which arise from this trial. So a common primary aim in a SMART is to compare two of those embedded dynamic treatment regimens at the end of the study. So here we're going to compare subgroups A and B with individuals who ended up in subgroups D and E at week 24 of the trial. So our goal for this work is to develop a sample size formula for the comparison of two embedded DTRs at the end of a study using a longitudinal outcome that is collected at an arbitrary number of time points. Now, because sample size is chosen for a specific analysis, we have to talk about what that analysis is. Here's one way to model data in a longitudinal SMART. So this is a piecewise linear model, and this reflects the sequential nature of treatment delivery in a SMART. So at baseline, we don't expect individuals to differ by assigned treatment, so there's just one mean. Between times 0 and 8, there are two groups, one for each first stage treatment. Then after time 8, there are now four groups, one for each embedded dynamic treatment regimen. Notice that we're only talking about four groups here, not six, because the model is marginal over engagement status, because these dynamic treatment regimens recommend treatment for both engagers and continued non-engagers. So remember that our primary aim that we're looking at here is a comparison of, say, this point on the purple line to this point on the blue line at week 24. So how do we fit this model? We're going to use what I call GEE type estimating equations. You'll see why I say GEE type in just a second. So if we start down at the end of the second line, we've got our usual vector of residuals here. We have a working covariance matrix and the Jacobian of our model, just like standard GEE. The top line is where things get slightly different. So now we're adding an inverse probability of treatment weight to account for the fact that engagers are randomized once, whereas non-engagers are randomized twice. The weight also includes an indicator that specifies whether a particular individual is consistent with a given embedded dynamic treatment regimen. We're also now summing over those embedded dynamic treatment regimens to capture the fact that engagers are consistent with two, non-engagers are only consistent with one regimen apiece. Then we sum over individuals, set that equal to 0, and solve. So now we can more formally state our goal here. We want to develop a tractable sample size formula for the test of the null hypothesis that the expected difference in potential outcomes between two embedded dynamic treatment regimes at the end of the study is 0 against some fixed alternative delta. The superscript here denotes the potential outcome under a particular dynamic treatment regimen. So using this model that we saw earlier, we can actually write this estimand as a linear combination of our model parameters, and those model parameters are asymptotically normal. So we can just use an asymptotic z-test for this comparison, and the variance here is just the variance of that linear combination of parameters. Var beta hat is the sandwich variance of the regression parameters from GE. The challenge in all of this work is to get a tractable upper bound on this variance in order to make for an easy-to-use sample size calculator. So under some mild working assumptions, and an exchangeable within-person covariance structure with constant variance across time and embedded regimen, this is our sample size formula. It can be decomposed into three parts. The first part is the standard sample size formula for a two-arm RCT. Small delta here is the target standardized effect size, which is determined in part by the fixed alternative hypothesis we saw earlier. 1 minus gamma here is the target power, alpha is the target type 1 error. The second term is an inflation factor that's associated with our SMART design. R here is an indicator of whether an individual engaged with first stage treatment. So this term ranges from 1 to 2 and can be thought of as trading off between a 2-arm trial and a 4-arm trial. So if everybody's an engager and this probability is 1, nobody's re-randomized, so we just have to have a 2-arm trial. Whereas if everybody's a non-engager and that probability is 0, everybody's re-randomized, so we've got a 4-arm trial. Finally, we have a deflation factor associated with the longitudinal outcome. Note that this is a deflation factor since we have within-person correlation and we're making a between groups comparison. This factor depends on the strength of the within-person correlation rho, the number of measurement occasions in stage 2, which is T2, and the total number of measurement occasions in the trial, which we're calling T. Our long-term goal for this project is to understand how to trade off between the sample size T2, and T in order to maximize power subject to a budget constraint. It's still early days for this, but this is where we're headed. So in the special case of 3 time points, where we have one at baseline, one measurement at the end of the first stage, which we're calling T star, and one at the end of the second stage of the whole trial, which we're calling T sub capital T, our deflation factor reduces to 1 minus rho squared. This is exactly the deflation factor that you'd see in a 2-arm pre-post randomized trial when you don't model a difference in means at baseline. And this work is published in Statistical Methods in Medical Research. So one strategy for generalizing this work to an arbitrary number of time points is to add measurements equally in both stages of the SMART. So here we're adding one measurement in the middle of stage 1, one in the middle of stage 2. And let's see what happens to our sample size requirements using this strategy. So here's a plot of the deflation factor on the y-axis versus the within-person correlation rho on the x-axis. A value of 1 on the y-axis corresponds to no deflation in sample size. Remember that this is a multiplicative deflation factor. So as we add time points in both stages so that the total number of measurement increases, higher values of t here correspond to lighter lines, we can see meaningful decreases in the deflation factor. So what this means is more measurement occasions gets us more power, or smaller sample size requirements. However, that impact starts to get smaller for large values of rho. So this is what happens when we add equally in both stages. We might also ask what happens when we distribute time points unequally across the stages of the trial. So here's a 5 time point longitudinal SMART. We've added measurements to stage 1 but not to stage 2. We could do the same thing where we add measurements in stage 2 and not stage 1. Or we could do a little bit of both. So let's see what happens when, with a fixed number of time points in the whole study, we start moving measurements between stage 1 and stage 2. So here we're looking at a total of 7 time points in the whole study, and we're increasing T2, the number of time points in stage 2 of the SMART. Again, the y-axis on these plots is the deflation factor, and 1 corresponds with no benefit to sample size. Let's look at the left plot first. The x-axis is again rho, and the dashed line here is 1 minus rho squared. This is the deflation factor for a 3 time point SMART. So you can see with 7 time points, we're always doing better than 3, as we'd expect. So as we shift more measurements into the second stage, so as these trajectories get lighter and lighter, they're increasing T2, we can see noticeable drops in that deflation factor again, so more power for small rho. For larger values of rho, it stops mattering, right? All of those lines are sort of on top of each other. We can see that pattern more clearly in the plot on the right. So here the x-axis is now T2, the y-axis is still the deflation factor, and the lines represent different values of rho. So as rho increases, as those lines get lighter, the lines get flatter, which indicates that shifting time points into stage 2 has less impact on power, right? The line for rho equals 0.9 is pretty flat. Curiously, there is some non-monotonicity happening here. So when T2 is large, so 4 or greater here, small values of rho slightly hurt you. The line for rho equals 0 is actually below the line equal for rho equals 0.3. We don't quite have intuition around this yet. So wrapping up, this is a work in progress. We're still in the process of building a user-friendly sample size tool that can abstract away some of the complexity in the functional form of that deflation factor for non-statistical folks. It's a fairly ugly function. We're also still working on developing guidelines for how to balance sample size and time points subject to that cost constraint. And we're still thinking about that non-monotonicity that I just mentioned in the relationship between the deflation factor and rho for large values of T2. As I mentioned earlier, the special case of 3 time points has appeared in Statistical Methods for Medical Research. The author-accepted manuscript is also on the archive. Finally, I'd like to acknowledge funding from the NIH and the Institute of Education Sciences, and you can find slides and other resources on my website, which is nicksewald.com. Thanks so much for stopping by, and enjoy the rest of your JSM.